All right, let's talk about solvents some more. SN2. We talked last time we were here, we talked about polar protic solvents, right? Things like water are polar protic, which means essentially they can hydrogen bond. Okay, polar protic solvents can hydrogen bond. That's one way to look at them. So alcohols are polar protic solvents because they can hydrogen bond. Amines are polar protic solvents, again, because they can hydrogen bond. Right? So polar protic, they can hydrogen bond, and they're not very good solvents. In fact, they're downright terrible solvents for SN2 reactions. And we talked about why, didn't we? What did we say? Why are they so bad at SN2 reactions? Right, they form a solvent cage, right? They surround the nucleophile. They prevent the nucleophile from wanting to seek out the electrophile. Are you with me? Because the electrophile has to be what charge?
Negative.
No. Positive or delta positive, right. And nucleophiles are? Or? Right. So, if those two charges don't want to collide with each other because the solvent's adding enough attractive force, they'll never meet, right? So that's a problem. So we have to switch to what is known as a polar aprotic solvent. Oops. Now, polar aprotic solvents are polar, but they don't have any protons that are attached to nitrogen or attached to nitrogen. Okay? So here we have very common solvent. You might want to write the name down and draw the structure. It's called acetonitrile. Acetonitrile is a very common solvent to do SN2 reactions because it's polar, but it's aprotic. It won't set up a solvent cage as efficiently as the polar protic solvents will. For example, acetonitrile is still polar, no doubt about it. So it can dissolve polar things. It just isn't very good at surrounding them. Okay? So now the nucleophile and the electrophile probably want to find each other because they'll be attracted to one another. Another common polar protic solvent that you're probably going to see is called dimethylformamide, DMF, it's abbreviated as. We almost always use the abbreviations, but just make sure you know what the abbreviations mean, okay? Because on a reaction, I might just write DMF under the arrow, and I'll assume that you know what it is, okay? So make sure you do. And here's another one, acetone. Acetone's also polar protic, so it can dissolve a good lot of things, but it's not very good at setting up solvent cages, okay? And another one that's not up there, it's called DMSO, dimethyl sulfoxide. It's also usable as a solvent for SN2 reactions, but it's not as nice because it's such a high boiling solvent. These three are relatively good because they're relatively low boiling. That one's kind of a bear to get rid of. But it can be used. So if you run an SN2 reaction, you're going to want to run it in this kind of solvent. So on an exam, for example, I give you, say, a bunch of reactions. The first thing I look for when I look for types of reactions is I look for the solvent. Is the solvent polar or is it nonpolar? And if it's polar, is it polar protic or polar aprotic? Now, it's not always a dead giveaway. It's not always a dead giveaway. But it's a really good suggestion. If I see these solvents, my mind starts going to SN2 reactions. But it's not 100%, but it's a very good indicator. Okay? So I see these solvents, my mind, SN2. Which is a one-step reaction, right? Second order, right? What's second order mean? Two reactants what? What about them, though? Right, so there's two things in the rate limiting step, right? So both reactants have to come together to form the transition state, is essentially what it means, right? So that's an SN2 reaction. Y'all with me on that? Okay, so we need to have polar aprotic solvent to make these reactions work really well. Polar protic solvents don't help out at all, or not very much. All right, here's another little thing that's kind of neat about these reactions. Crown ether. Now, let's say we want to do like this reaction right here, this simple little reaction right here. KF, potassium fluoride, a little bit of acetonitrile, and they have this thing called 18 crown 6. Now that's a crown ether, is essentially what it is. They all have similar structures to this. Now, what's going on when you add a crown ether? Well, let's just think about what's happening in the flask. We add sodium fluoride to the reaction. It's in acetonitrile, so it dissolves up. Let's imagine, I'll pick on you because you sit in the front row. Let's imagine you can be the cation because you're positive and I'll be the negative one, okay? Thank you. Now, we're in this solvent. We dissolve, but she's the most positive thing in the solution. I'm the most negative thing, right? So we kind of want to hang out because she's very attractive and I'm very attractive. So we're dissolved, but we're kind of close to each other. And, well, that electrophile there is not very positive. This is very positive. You guys over here aren't that positive, so I'm just going to hang out here. You know, I'm not going to bother reacting with the delta positives over here because this is so much more attractive. So I'm going to stay here. We're going to float around and do like whatever we do, right? But that's not going to make any money, right? That's not where the reaction has to go. I have to react with somebody over here, one of you delta positive people, right? So somehow you've got to get me, the nucleophile, convinced not to hang out with the positive charge anymore. Are you with me? So we have what's called a crown ether. Well, now, what does a crown ether do? You can think of it like this. You can think of it as it's a dragon that's going to come and take the cation away from me. So now my cation has been, if you will, sequestered or taken by the crown ether. So now she's hanging out with crown ethers because, you know, they're delta negative. I'm all by myself now. I don't have any positive charges to hang out with. Are you with me? So I got no choice now but to associate with the delta positives over here. I have to now because my positive charge is gone. Where did it go? It literally is in the middle of the crown ether. It's in the center of it. Being attracted by all those little oxygens all the way around. Are you with me? So now I have to associate with you guys. And guess what? Instead of colliding with the positive charges, I'm colliding with you guys now. So that's going to make the reaction go faster. Doesn't that make sense? I know it's a little subtle, but it makes sense, right? You get rid of my positive charge, it forces me to interact with the delta positives more often, right? If I have to interact with you guys more often, we're going to react more. We're going to hit more often, which means we're going to react faster, right? So,
Yes.
Oh, okay. Now, you don't have to worry about the sizes of the crown ethers, but they all come in different sizes. 18 crown 6 is designed for potassium. There are larger ones that are designed for cesium and rubidium, and there are smaller ones that are designed for sodium and lithium. Okay? They're specifically made for certain cations. Okay? Because they can literally just grab them and take them away. And that forces the nucleophile to have to react with the electrophile. Well, I shouldn't say it forces it to. It encourages it strongly. Leaving groups. We already talked about leaving groups, right? What's a leaving group? What side do they go to? They go to the leaving group, right? Because the leaving group leaves and takes the bond electrons. There you go, you got it. Takes the bond electrons with it. Now, does it make sense to you that some leaving groups are better than others? Yeah, it makes perfect sense, doesn't it? Some things would be better off on their own, some things would be worse off on their own. Does it make sense to you guys that water is one of the best leaving groups? Yeah, water is a pretty stable molecule on its own, right? So if a molecule can dish off some water, it's probably going to do it, right? You give it half a chance, it'll throw water out, right? Because water is a good leaving group. How do we know it's a good leaving group? We know very well it's stable because, you know, it's everywhere. Yeah? But what else is a good leaving group? Well, we talked before. A good leaving group, is the conjugate base of a strong acid, right? Anything that's stable as a negative, for example. So good leaving groups, first of all, you've got to talk about halogens. Chloride, iodide, bromide. Those are all great leaving groups. Very, very nice leaving groups. Because all three of them are conjugate bases of strong acids, right? Right? Now, here are a few you haven't thought of. Where R can be a lot of different things, but let's just leave it as just R for now. That's a great leaving group, actually. Now, I want you to start, and maybe you are already doing this, so if you haven't, please start doing this. Start looking for analogies, because chemistry is all analogous to itself. So there are some things I know, and I know for sure, and there are other things that I can use and draw analogies to. For example, what does this kind of look like? And let's draw another one that's slightly different, but very similar. This is also a good leaving group. What do these things look like? Like if I said, tell me something that you already know that these two bad boys look like, what would you say? They're like, what? I don't think so. There's no carbon. They look like sulfuric acid, don't they? They look just like sulfuric acid. Sulfuric acid is this. You all should know this. That's sulfuric acid, is it not? You don't see the similarities between this one and this one, this one and this one? You don't see the similarities? Or you do? Yeah. They're obviously similar, right? Right? One more time. Are they or are they not obviously similar? They're not the same. They're similar. Right? So does this, you guys all would say, if I said, hey, is this a strong acid? You guys would have instinctively yelled out, yes, strong acid. Here's its conjugate base. So now, cover that up. Looks like those two, right? All you're changing is what's out here. Make sense? So if I asked you a question on an exam and I said, okay, is this, oops. Is that a strong acid? What would you guess? Would you guess it's a strong acid? I would. I would guess it's a very strong acid, right? Why? It looks just like this to me. In fact, I'm going to go out on a limb and say it's probably a better acid than this. For reasons I won't want to discuss, but I think it probably is better, right? So this anion over here, if I put a CH3 here, this is going to be a stable anion, right? Right? We got to go back over acid-base theory? Say no. Thank you. Right? Okay. So these are conjugate bases of strong acids. If you don't believe me, prove it to yourself tonight, or preferably before Halloween, because after Halloween, God only knows what will happen. You guys are such a tough audience. Now, good leaving group, conjugate bases of strong acids. Okay? Now, yeah? Depends what I ask you. But yeah, for now, yeah, that's fine. Okay. Now, those are the anion types of leaving groups. The other type of leaving group that you do see from time to time are the neutral molecules. For example, water is a good leaving group. NH3 is a good leaving group. What else we got there? Sulfides, amides. To a lesser extent, you don't see these very often, but they are good leaving groups, but they're very rare. It's usually water, alcohols, or amines that you see as good leaving groups, and they leave as neutrals. Okay? In this class, we're going to see water and alcohols behave as leaving groups. In organic 2, we'll see amines do it. Okay? Anything that can leave as a neutral is usually a good leaving group. Oops. Okay, so let's just draw a quick reaction. CH3 chloride plus, I don't know, how about a fun one? How about sodium cyanide? Yeah, there we go. DMSO there you go. So there we go. There's an SN2 reaction. While we're here, can anyone draw the Lewis structure of sodium cyanide? You can?
I could try.
Go.
No, I don't want to do that.
Oh. Wait, why not? Yeah. You can do it?
No, mine goes with battery threats.
Oh, okay. Can you draw the Lewis structure? First of all, what kind of molecule is that? Is it a ionic, covalent? What? It's what?
Ionic.
It's ionic. So what does that mean? What does it mean to be ionic? What does it mean to have an ionic bond? Who's talking? Someone's talking. I can't hear what you're saying. I'm sorry. I really can't hear you.
Transferring an electron.
Yes, that's the process they go to get there. But what does it mean once you're there? What? I get that, but what's the result of all that?
Ions?
Ions. What kind?
Positive and negative.
Right, cations and anions, right? So what's the cation in sodium cyanide? Na, right? So I'm going to draw Na as a positive, right? Does that make sense? So the cyanide's negative, yes? Everybody agree the cyanide is negative?
Yeah.
So that's sodium cyanide. In sodium cyanide, just the molecule of sodium cyanide, do you think sodium cyanide is an electrophile or a nucleophile? Or neither?
No.
It's an electrophile?
Oh, and then
Who said? Someone said nucleophile over here. Why did you say that? You're right. Why did you say it?
Because of the negative?
Because of the negative charge. Right. And we know sodium is a pretty good spectator ion. Doesn't really get involved in much, right? So probably the cyanide, Cn minus, is a good nucleophile. Is it the carbon or the nitrogen that's nucleophilic?
I'll say the nitrogen.
Why would you say the nitrogen versus the carbon?
Because the nitrogen is more negative than the carbon.
Is it? Are you sure about that? If you count
They're pretty much the same.
If you,
actually.
but
They're like
if you count formal charge, though, you'll see the carbon is negative. Right? The nitrogen is neutral. The carbon's actually negative if you count formal charge, right? So the formal charge on cyanide is on the carbon.
Okay.
Does that make sense to y'all?
yes.
Okay? So you're right, it is a nucleophile. Most definitely. It's nucleophilic at carbon. So the carbon is going to do all the reacting. The nitrogen is just along for the ride. Are you with me on that? Cyanide is one of the best nucleophiles I can talk about. I love cyanide. Not because of the bad medicinal properties of it. I said bad medicinal properties. In other words, it'll kill you. Right? Because it's really, really, really good. Why is it good? First of all, it has a negative charge. It has a pure negative charge on carbon. That's really good. It's a good way to add carbon to a molecule because it has a carbon that has a negative charge on it. And it's cheap. You can buy it by the truckload. You shouldn't. Because I'm sure you'll get on a watch list. It's probably true. Now, but here's the other reason why it's really interesting and why it's really good. It's linear. It's linear. So it's like an arrow or a heat-seeking missile or however you want to describe it. It's short, it's small, and it's linear, and it's negative. These all add up to being really good things for nucleophiles. Now, why is it important that the nucleophile is small? Let's imagine that I am the nucleophile, and I'm a pretty big dude. And I have to get back there, and I have to react with you guys in the back, right? That's where the electrophilic carbon is. It's back there somewhere. I got to get through all this stuff, all this preamble before I can even react, right? So if you're tiny, say you're just a little toddler, right? That high. A little toddler can go back there and give you guys a high five in less than a second, right? Because they're small. Me, I'm going to, excuse me, pardon me. Sorry about that. Oops, sorry, pardon me, excuse me. Oh, and I get about here, and Rachel's like, no, you can't go any further. I'm not moving. I'm like, oh, I'm going to go around the other way. Rachel's, blocks me again. See, I know your name, so I pick on you. So you see how this works? Smaller is better, because smaller can get through this mess of stuff to get to the electrophile. Are you with me? Now, does it make sense then, if, say, Tyler there is the electrophile, does it make sense that if all this stuff wasn't in front of him, I could get to him faster? That makes sense too, right? So it seems that we're getting into an issue with steric hindrance, right? It seems that we're getting into an issue with steric hindrance. And SN2 reactions are very sensitive to this. Very sensitive to this. If your electrophile is too big, if your nucleophile is too big, things ain't going to work. They're going to come to a complete and abrupt stop. Now, let's take a look. Methyl halogens react the fastest. They react the fastest. Primary halogens react second fastest. Secondary reacts a little bit slower than that. And do not react. Tertiary halides do not react. Now, I did a little crying there, because that's one of the most common questions I throw in exams and quizzes, and one of the most common questions people get wrong. I'll give you a beautiful SN2 reaction, just telegraphed. Got polar aprotic solvent, got sodium cyanide on top, and everyone's like, yeah, SN2 reaction. And then I gave you a tertiary halide just to throw you off the scent. And everyone draws the product, everyone draws the mechanism, and their answer is no, the correct answer is no reaction. So you get all this beautiful schemes of mechanisms and all this nonsense, and I just give you 0. It's completely wrong. Because it's a tertiary halide. There is no reaction. Are you with me? Okay. So now, methyl is the fastest. Let's consider a methyl molecule, or a methyl group. Now, in order for a reaction to take place, let's have some fun. I need 4 volunteers. 5 volunteers. Yeah, 5 volunteers. Come on down. See, Jesus is brave. Come on down. I don't know your name. I'm sorry. Shawnee, everyone. See, no one wants to give you guys a round of applause. I would have. Come on. I'll just pick you if you don't come up here. Here we go. 2 more. Come on, Ian. You're always good for a laugh. All right. So here we go. We're gonna simulate an SN2 reaction. Ian, if you would please, you could be my halogen. If you would please, you can be the carbon that contains the halogen. So you guys just hold on like that. Now, if you would please, face Ian. Okay. Now you guys just stand off to the side real quick. Okay. Now, what's your name?
Jessica.
Jessica here is a methyl group. She's got hydrogens coming off her back. Are you with me? That's where the hydrogens are. Ian's in front of her. The hydrogens are coming off her back, right? I'm going to be the nucleophile. I'm going to be the one that's on the hunt. Are you with me? Now, whenever a nucleophile has to attack an electrophile, it has to occur this way. Remember the orientation part of a reaction that we haven't really talked about yet? We're talking about orientation now. Remember we talked about in class how sp2 orbitals are like this, right? And they have a little nubby thing back here. We didn't really talk much about the little nubby thing until the other day. And I said when a nucleophile attacks, it has to attack that nubby thing. Remember we said that the other day? If you don't remember it, review your notes. That's where the electrons have to go, right? So right here, Jessica and Ian have got their sigma bond going on right here, and the little nubby part's back here between her shoulder blades, right? So the nucleophile, if I'm going to attack her and have the reaction work, I have to attack her. I'm not going to hit you. Wham! In the back. I have to hit her in the back. Why? Because that's where the orbital is. Are you with me? And when I do that, Ian has to leave. Why? Because now I'm making a bond here. Ian is gone. Okay? Are you with me on that? So, clear path, hit her in the shoulder blades, Ian leaves, reaction's over, SN2. Are you with me? Now, Ian, make your bond again, please, with Jessica. Now, we can have you, Miss Ahmed, come in here, and you can use this to hold hands with Jessica. Okay. Methyl group. Big methyl group. Bigger than hydrogen, for sure, right? Bigger than hydrogen. Now, again, I have to get to Jessica's back. So come back here just a little bit. See how she's in behind her now, right? So now I have to, oh no, you were good. Just one step forward. Right there. Don't move. Now, she's got 2 hydrogens over here and a methyl group right there. So here I am, the nucleophile. And remember, we don't think. We just collide blindly, yes? So now it's like she's got a guard out front. It's like a pit bull, right? So I try to get in there to do the shoulder blade thing, and no, I can't get in there quite as easily. Why not? Because now I got to move around this bulk, this methyl group. So I'm going to go slower, right? By definition, I have to go slower. Why? Because now there's something in my way that I have to maneuver around. Are you with me? Everybody get that? Let's do one more. Would you like to go hold hands?
Go where?
No, over to the other side. Just put your hand on, if we can, right here, please. Just right here. Is it okay if you put your hand right here? Is that okay?
Yeah.
All right. Now, again, I'm the nucleophile. I have to hit her between the shoulder blades. But look, there's a lot less room. It's closing in. You see what's going on? Everything behind Jessica is closing in. That's the only place I can attack her is from behind. If I hit her from the front, it ain't going to work. It's got to be behind. Whoosh, then Ian will leave. One more. Jesus, come and stand right here. Now look, there's no way I can get to Jessica. I can't get there. There's physically no room for me. No matter how small I get, there's no room at this location. So this is tertiary. There's literally no room for the nucleophile to get to the electrophile. Are you with me? All right, thank my young folks here for being the best little actors I ever had. Thanks, guys. Appreciate it. Does that make sense to you guys?
Yeah.
No, I think the people who actually do these little skits, I think they remember it better than anyone. Especially poor Jessica, because we're just beating her up. Jessica was terrified that I was going to smack her in the back. Go ahead.
The fact that the tertiary carbon and the secondary carbon have hyperconjugation.
Be careful with that. That's a great comment. Save that for SN1, because that's going to come into play there. Very good. Good comment. Very good. Now.
Wait, before you continue. It has to attack the little nub
Yep.
of the SP, but the little nub, isn't that what's attached to Jessica, the carbon?
No,
And then the
no.
big-
It's behind her. The big part of the sp3 orbital is part of the sigma bond, right? And the small little nubby part, we used to never draw it because it was always a big mess where the carbon was, but it's still there. So when a nucleophile attacks, it actually puts its electrons in that little nubby part of the sp3, and then the whole thing kind of switches a little bit.
So the carbon is like in the middle of the big balloon and the little nub.
Yeah, the carbon would be like, say, right here. The protons would be right in here somewhere.
So they're sticking, the little nub's sticking out.
Yeah. Remember, this is a node right there, so it's probably where the nucleus is, right? All right. Now, that whole thing where the nucleophile has to come from in behind the electrophile, right? That's got a name. We use the name all the time, and you're going to giggle, so let's get that out of the way right now. It's called backside attack. There you go. Take a minute. It's called backside attack. Now, backside attack. That's where the nucleophile must come from the backside of the electrophile. In other words, it must come from the opposite side of the leaving group. Has to. Backside attack. Yep. Comes from basically the opposite side of the leaving group. Yeah. That's because the chlorine is going to be the leaving group, right? And the little nubby part of the orbital is 180 degrees from it. Okay? So, yeah. So now, the cyanide, or whatever the nucleophile is, when it's methyl, there's, the hydrogens aren't zero. They have some bulk. But there's quite a bit of room to come on in here and attack that carbon from the backside, right? So it's just going to kind of happen. It's going to happen probably really fast. Just like that. And that's probably going to happen pretty quick. There's not a lot of bulk in behind there. So now, that's pretty cool. But now we're going to add another methyl, right? We're going to take off one of those hydrogens, go from being a methyl halide to a primary halide. Are you with me? We're essentially putting a methyl group on that thing. So by doing that, now I'll draw it to the best of my abilities here on the board. And I have a slide I'll show you in a moment. So here's my methyl group, right? Just by drawing it, I think, on the board, just nice and quick and simple, you can already see that these hydrogens are starting to impede on the path of that cyanide, right? They're starting to get in the way. Okay? Now, the cyanide can still kind of weave itself in there and make an attack, but these methyl groups are certainly going to slow it down a little bit, right? It's like when you play soccer or something, there's always defenders in front of the goalie to slow the attacker down, right? It's kind of what they're there for, I won't say anything more. Did you ever have something go into your head where you just shouldn't say it, so you just let it go? back into the dust. Yeah, go ahead.
I don't know if this is what Eric was asking, but we talked about, we were asking about conjugation, but induction, wouldn't that make that the H is more delta positive? So
Yep.
You're going to be more likely that
Keep that in mind.
That is what he was asking.
He was asking about hyperconjugation and stuff, but all those two things you guys are talking about are going to come into serious play in SN1 reactions, so don't forget them.
But it doesn't affect this?
Mhm.
And distribute the electron density
Yep.
around the molecule so it really has to attack.
No, the carbon will still be the most delta positive thing because induction, after every bond, induction gets less and less. But it will spread the charges around, and keep that in mind because that's going to be a real big deal. Now, the only reason we're not talking about it just yet because we haven't talked about the E reactions yet, E1, E2. When we get there, everything you guys are saying is going to come into play. Okay? And you guys are already starting to think, well, couldn't it also do this? And you're right. It's a competing reaction. But we don't want to go there just yet. Okay? Good. Very good for both of you. You know what? Self-high five. Good job. Very good job. Okay, so you can see adding just another methyl, making it primary, slows everybody down, right? So I hope, at least I think, it's becoming a little bit obvious that if I make it secondary, things get even worse. There's more hydrogens in the path. There's more stuff blocking my nucleophile from getting to the electrophile. So this reaction is going to go even slower. Now it will work. SN2 reactions on secondaries do work, but they work very slowly. You may even have to heat it up. Now, if you put a tertiary, I'm not going to draw because it'll get messy, but if I put another methyl group on this hydrogen, take this hydrogen away, make it methyl, the whole backside of this carbon gets obscured. You can't even see it. Okay? So, primary methyl is the best for SN2. Primary is second best. They both work very well. Secondary, well, things start to get a little slower, or a lot slower actually. Tertiary, not at all. There will be no SN2. Okay. There it is. That's what I want to show you. So now, let me show you what I'm trying to show you here, but let's do space filling models. Remember space filling models? Okay. So here, the blackness here, that's the carbon, that's the backside of the carbon. So this is a big leaving group here in orange. So you have to attack it from here. Now, as you can see, with a primary, that black part of the carbon is already obscured. It's already becoming less. Okay? And as you add a secondary, so you add two methyls, there's even less room for a nucleophile to attack. And here's the space filling model for a tertiary. You can't even see the black carbon anymore. It's like the carbon is not even there. So the nucleophile literally can't get to the carbon. Okay? So, let's review. SN2 reactions. The nucleophile must attack the electrophile, the leaving group will leave. What's the first thing you look for? Solvent. Look for a polar aprotic solvent like DMF, DMSO, acetylnitrile, acetone. What's the next thing you look for? Well, you can look for a leaving group. Sure, why not? Look for a good leaving group. Then you look to see if it's primary, secondary, tertiary, or methyl. Halides. If it's primary or methyl, SN2 all day long. Secondary, probably going to do an SN2. Tertiary, ain't no way it's going to do an SN2. They just don't do it. Okay? And then you can look for the nucleophile as well. Make sure there's a nucleophile in the reaction.
So you're looking for a polar aprotic.
Polar aprotic solvent. That's the first thing I look for. And when I see that, then I start looking for the nucleophile and the halide. Start looking for both.
Look for a nucleophile and halide?
Yep. Make sure the halide is not tertiary. That's the number one thing. Make sure the halide is not tertiary. Because if it is, it will not react.
And if it's a non-polar solvent, you can still do it SN2 with a non-polar solvent.
No, non-polar solvent wouldn't be able to. Well, I shouldn't say no. It may, but not likely, because you have to dissolve the nucleophile and the electrophile. And by definition, they have to have charges. So probably won't work. All right. Isn't this fun? Stereochemistry of an SN2 reaction. Write this word down, or this phrase, Walden inversion. Walden inversion. SN2 reactions are interesting, and they're interesting for a number of reasons, in my opinion. But here's a really spectacular thing, I think. If you have a chiral molecule and you do an SN2 reaction, you'll get what's called inversion of stereochemistry, which means if you start with an R, you're probably going to end up with an S, which is, I think, kind of neat. Now, let's take a look at that. Let's draw, well, we'll use their example. Why not? Carbon, bromine, and was it hydrogen on top? Hydrogen on top, then we do methyl group here, CH2, CH3. There we go. So that, according, we'll just steal it from there. That's going to be an S enantiomer. Okay, and we're going to attack it. Now let's use a different nucleophile. And in case you haven't noticed, I'm trying to use these examples to introduce nucleophiles, right? Let's use something called sodium azide. There we go. That is azide. It's a very good nucleophile. Again, like cyanide, it's linear and it's negative, overall negative. So these nitrogens on the ends are nucleophilic, right? It's a great way to introduce nitrogen into your molecule. Okay? Now, the azide is nucleophile. It's going to attack from the back side of the carbon. This is a secondary substrate, or secondary halide, so it's probably going to react pretty slow, but it will react. And that's an SN2 mechanism, right? Nucleophile attacks the carbon, the leaving group leaves. That's classic. Now, remember the transition state we talked about the other day. Oops. So there's my transition state. It's a classic SN2 transition state. Now watch what happened. You went from being tetrahedral here, right? To now, the intermediate, this carbon is kind of flattening out, isn't it? Okay? Notice how these methyls and the ethyl were both pointing in that direction, weren't they? But in the transition state, they kind of went like that. They kind of went from here, transition to here. Now what's going on? Well, don't forget, there's a pair of electrons coming in here, right? These are also electrons, these bonds. They don't know what this is. They just know that negative charge is coming into their vicinity, right? So they're repelled by it, so these bonds here actually literally move away from it, right? Does that stand to reason? They're facing this way. Negative charge comes in, so they are repelled by it. They move away from it. Does that make sense? So now as this bond is forming and this bond is breaking, so the bromine is leaving as bromide, right? The negative charge that's here is actually moving away, right? So you're repelled by this negative, these electrons that are here, but they're leaving. They're going away. So now you can come this way, right? You started over here. You got some negative charge, negative charge, negative charge. Oh, relief, relief, relief. Okay, because this is leaving. Don't forget, that's leaving. The bond electrons are going with it, right? So electron density is coming in here and leaving here. You all with me on that? So these groups, whatever these groups are, they don't have to be methyls or hydrogen, whatever these groups are, they start out this way. They go flat, make it like a planar structure here, and then they keep on going this way. And the result of that is this. There we go. Notice the methyl and the ethyl, the methyl and the hydrogen that were once facing that way are now facing that way. And if you count the stereochemistry, you're going to see this is R. Started out S, did a reaction, we ended up R. It's called Walden inversion. Probably because Walden was the first person to discover it.
We have to add like plus bromide to finish that off.
No, you can if you want. I mean, I'll do it for you.
Is that why linear matters for nuclear cells, so that it's not?
No, linear matters because it makes them small. So they don't have a lot of bulk. We're going to get into bulky things soon enough. So that's Walden inversion. Yeah?
Or, I don't know, like the formal charge
Yeah.
for the 18.
Yep.
Are they wrong or something?
No, they're not wrong.
No?
No.
They're like that. Okay.
Yep. Count them.
Yeah.
Yep. It's a good exercise to try at home if you're having trouble. Just count them when you get home. Make sure I didn't screw up. I didn't, I promise.
Yeah. Okay.
I didn't. Okay, so that's Walden inversion. Every SN2 reaction does that. They all do it. And they do it 100%. So if I have 100% S, when I'm done, I'll have 100% R. You with me on that? This is how it works. And it does it because electron repulsion from the nucleophile pushes the groups the opposite direction. Oops, and we talked about backside attack. Clean page, please. SN2's little cousin.
The nucleophile push, you said the bond to the other direction?
Yes.
The bond.
Yep. Has to, because, it's Vesper theory, right? Valence shell electron pair repulsion. So as the negative comes in, the bonds have to move away from it. Because the bonds are negative. Well, they have electrons in them. SN1. The far more interesting reaction, in my opinion. So, of course, it's opinion. Just opinion. So you know what that means, right? If I think it's interesting, it must be more difficult, right? Yes, it is more difficult, but only because it's really freaking cool, right? Now, what does it mean to be first order? One molecule in the rate limiting step. That's peculiar. I wonder which molecule is the most important in an SN1 reaction. Let's draw one. Let us draw an SN1 reaction, shall we? Yes, Dr. Bates, we'd love to see an SN1 reaction. All right. I knew you'd be excited about this. I was wondering what to get for your birthday. I thought an SN1 reaction. All right, let's do a classic SN1. Bromine, whatever.
SN1 means the same thing as first order?
It means substitution, nucleophilic, unimolecular.
First order is just...
The one means first order, or unimolecular, first order. They both, they mean kind of the same thing. And then here we will put in, say, some methanol. Notice I added a polar protic solvent. Not polar aprotic, polar protic. Methanol. There we go. That's a classic SN1 reaction. In fact, now that you've learned, well, you haven't learned the SN1, but you've heard about it now. Common quiz question, common exam question. You've heard of SN1 and SN2 reactions, period. Provide an example of each one, draw the mechanism for each one, draw the reaction diagram for each one, and show me the transition states, if any. I know, I'm such a jerk. I know, right? I'm such a jerk. It's like I want you to learn. But don't worry, you'll be able to do it. It's not that hard.
Are you serious or joking?
Absolutely serious. Every student that comes through my class can do that. Plus, they can do the E1 and the E2 as well. It's not that hard, trust me. Okay, well, this is interesting, isn't it? So, we know it's not SN2. There's two things that tell me right now that reaction is not SN2. What's the first thing you notice?
Solvent.
Solvent, polar protic, which is not an SN2 solvent, right? What's the next thing you notice? Tertiary halide. Well, that kind of gets rid of the SN2, doesn't it? What's the other third thing that's probably a little bit subtle?
H and BR, you know that thing is second, like you'd have to first break it and then make it?
Yeah, kind of, yeah. I was thinking there's no nucleophile. There doesn't seem to be a nucleophile, right? Because remember we said nucleophiles had negative charges, right? We never talked about methanol being a nucleophile. That's peculiar, right? Well, we know it's first order, right? Because I'm telling you it's first order. So if it's first order, that means there's one molecule in the rate limiting step. Are you with me? There's one molecule in the rate limiting step. So that means that, well, all right, time out for just a second. Let's just talk about one quick thing. This is rather confusing, isn't it? Where'd that oxygen come from?
From the solvent product.
Comes from the solvent, right? It has to come from the solvent. There's no other source of oxygen. It has to come from the solvent, right? But we know that that solvent is not going to attack that carbon in SN2 fashion. It's just not. Okay, so, okay. Oh, no. Well, we know that okay, well, if I'll give you some details about the reaction. If I double the concentration of the alkyl halide, the reaction goes twice as fast. So that means it's first order, but it also means it's first order in regards to the alkyl halide, right? It's not the methanol that makes it first order, it's the alkyl halide, right? So the alkyl halide is in the rate limiting step. Are you with me? Not the methanol. The halide is in the rate limiting step. Okay, so the halide is going to do some kind of magic thing, and then things are going to happen. You with me? What's the one thing you think the halide can do? Maybe. You mean just throw it out? Let's keep talking.
Makes a bond with the OH, or
It will, but how? You said leave. What do you mean by leave?
takes the bond electrons.
Who does?
Halide.
Aha! The halide. What about that? Which part of the halide? You're right there, man. You're right there. You're like, the next thing you say makes it right or wrong. No pressure. Who's going to take the bond electrons? Who's going to take them? What's the leaving group on there? Bromine. So is bromine going to be a leaving group? It usually is, right? So it's going to take the bond electrons. Make sense? Very good. So Michael says, right, Michael? Okay. Where's David? David. Yeah. I keep calling him your name. I think I called you his name once or twice. Good. It would have been really embarrassing for me. I think I called you his name like 5 times in a row, like while you're still in the same conversation. It was terrible. No, it was in the hall. He thought it was terrible. I just kept calling him Michael. And he kept saying, my name's David. I'm like, okay, Michael, whatever you say. Are you sure about that? Anyway, don't be, I'm sorry. I really am embarrassed by that. Anyway, so the leaving group's going to leave, right? Now, okay. There you go. Carbocation and a bromide. This is neutral on this side of the arrow, right? This is also neutral on this side of the arrow because they have a plus and a minus, right? So it's still neutral on both sides of the arrow. Okay? Now, nothing wrong with that. Nothing wrong with that at all. It's a tertiary halide, right? So it's tertiary carbocation, right? And you know those are pretty stable compared to methanol and all that, right? So that's probably not so bad, right? Plus it's in a polar protic solvent, right? A polar protic solvent should be able to form a solvent cage around the bromide, shouldn't it? So it'll take the bromide and form a cage around it, right? And we know, because the bromide will have a solvent cage around it, that so will this, right? It's cation, right? So we know, let me get a... And you get the idea, right? It surrounds the bromide. So the bromide, you can kind of imagine, is being kind of drawn away from that cation a little bit, right? And the cation, same thing, right? The O minuses are going to face the cation, right? So that's kind of what's going to happen. This is going to get surrounded by the O negatives of the methanol, and this is going to get surrounded by the H's of the methanol. But isn't that convenient? Because don't we have to make a bromine hydrogen bond? Isn't it convenient that they're being attracted to each other? Isn't that neat? And isn't it convenient because we have to make a carbon-oxygen bond, right? Aren't these carbons and oxygens attracted to each other? Are they or are they not? Isn't that cool? Isn't that neat? I told you everything you need to know, right? And now it's kind of all coming together. No, I didn't think any of you get it right. Michael, I'm very impressed you got it right. Self-high five. There you go. That was impressive. It really was. So that's how it happens. First things first. The bromide leaves the halogen.
Now, what initiates that?
Heat, usually. But it can also do it at room temperature. It doesn't have to be that hot. Okay? Now, here's a fun fact. Let's imagine I'm the bromide. Ian, you can be carbon. So we had our nice little bond there. Don't hold them so tight. I can take them from you in a minute. So here we have a nice little bond, right? So then I'm going to take the electrons, right? But then I'm going to go back. Why did I go back? Because he's positive, I'm negative. We're going to react, right? Make sense? Gone again. Whoop, back again. Didn't like that situation very much. Gone again. Back again. Gone again. Back. We're going to do this probably 1,000 times, right? Until eventually the solvent can pull me away and get in between us. Does that make sense? Because I'm like, when I leave Ian, I'm still right physically here. He's still right physically there. So why don't we just go back to where we were? Because Ian doesn't want to have a sextet. Because, he's a carbon. He likes octets, right? So as soon as I take the electrons from him, he wants them back. So he attracts me because he's positive. But then the solvent sneaks in. And instead of me giving my electrons back, give him the electron. You're the solvent. Solvent gives them to Ian. And I'm left on my own. Oh, no, don't let go. You're the solvent. Are you with me? So I was doing it, and then all of a sudden solvent snuck in and gave it. Instead of me giving my electrons to Ian, the solvent gave the electrons to Ian. Ian does not care where the electrons come from. Why not? Because he just wants an octet, right? Me, now I'm bromide, yeah? I'm okay on my own because I'm bromide. I can float around in here all day until I get a hydrogen, right? Does that make sense? Thank you, guys.
Even if it's negative,
Thank you.
Huh?
Huh?
Even though it's negative, it can still flow by itself.
Yeah, it's a leaving group, like sodium chloride. The chloride and the sodium float freely in water by themselves. Surrounded by solvent, of course. Yeah, surrounded by solvent, right. They're not ever by themselves. That's gas state reactions. Those are more interesting. Okay, so you form a carbocation, it gets surrounded by oxygen. Now, what's going to happen, I'm just going to erase these solvent molecules. It's really hard to draw the solvent in like that, like I'm showing you, because it kind of gets cluttery real fast. So you don't normally draw them in. We just accept that they're there. Okay? Now, if on an exam I ask you to show them to me, then you want to draw them in. But if I don't, if I just say draw the mechanism of this reaction, just go ahead and draw the mechanism as I'm going to show you now. The bromide leaves. You get the carbocation in the leaving group. At this point, the solvent, whatever the solvent is, attacks the carbon, fills in the octet. Okay? All right. Now, where were we? Okay, here we go. First of all, before we move on, before I attack that carbon, what's the structure of that carbon? Is it sp3, sp2, or sp? It's sp what? So what's the structure? Is it what's the molecular structure? Trigonal, planar. Very good. It's planar, so it's flat. All right, very good. And then it goes back to tetrahedral, right? All right, analogy time. Open your mind up. Let your mind kind of be open here, okay? What is, well, here's the question. I'll ask you the question in a very simple way. How acidic is that proton and why? What is this whole large thing analogous to? Something you've seen before?
Is it like a resonate?
No. Something that you've learned in general chemistry and you haven't forgotten about since. What does it look like? Very simple molecule that you know the name of. Starts with an H. I mean, it's analogous. It doesn't look that much like it, but it's analogous to it. Another molecule where oxygen has a plus charge. What? Not hydroxide, the other one. Hydronium. Looks kind of like hydronium, doesn't it? Hydronium is this, isn't it? That's hydronium, right? Take off these two hydrogens, put this group and that group on there, it's the same thing, right? So I'm not saying they're the same. They're not the same. But they're analogous. Everybody in here is going to say this is a strong acid. Right? Is hydronium a strong acid? I heard of course it is. So then that must also be a strong acid, right? Because they're analogous, aren't they? You draw an analogy between the two. So that means this proton can come off pretty easily with bromide. This is the only time you're going to see halogens act as bases is when the proton they're extracting is very acidic. And that's how you form the HBr. And there you have the ether at the end of all this. Start trying to draw analogies from what you're learning to what you've already learned. I know it's hard. I'm not saying you can do it right out of the gate, but try to do it. Try to think of things you've already seen and relate it to what you're learning now. That's what science is. All right. And that is your first example of an SN1 reaction. Now you're probably thinking, and I will be glad that if you thought this, that's not all that interesting. You're right, it's not really. But there are some things we haven't learned yet that will come up next time. And then you will think, these are the coolest gosh darn reactions that ever walked the face of the earth. All right, guys, we'll see you next time.